Hello everyone, my name is Sahil,
My name is Manan.
and today we are going to present our OS research review paper summary on the topic deadlocks in operating systems.
So now we will be starting with our first research paper, which is deadlocks. Deadlocks in an innovative method designed to detect deadlocks in shared memory system effectively. The method uses a digest instead of simple Boolean lock, allowing for dynamic and flexible detection. It is compatible with main types of spin locks, which makes it highly versatile in various applications. Deadlock is proven to be more efficient than traditional methods, helping to save system resources and reduce errors. Experiment test demonstrate that it matches or exceeds the performance of older detection methods. The algorithm has potential application in software transitional memory systems offering wider utility.
The second research paper explores hardware-software integration for improved deadlock detection and avoidance in MPSoC systems. MPSoC is multiprocessor system on a chip. It introduces two hardware units. The first is deadlock detection unit and the second is deadlock avoidance unit. The deadlock detection unit accelerates deadlock detection and it boosts the application execution speed by 46%. The deadlock avoidance unit prevents deadlocks while improving the execution speed by 44% with minimal chip usage area. As MPSoC designs grow more complex, software based deadlock management becomes insufficient. Hardware based deadlock management ensures better reliability and reduces system bottlenecks. The paper presents architecture details and experiments demonstrating the unit's effectiveness in reducing execution time.
Now we will be discussing about our third research paper, which is on deadlock detection in distributed databases. The paper discusses various methods for detecting deadlock in distributed database systems. It introduces a model that categorizes deadlocks ranging from simple cases to more complex ones. The research reviews four primary detection methods: path pushing, edge chasing, diffusing computations, and global state detection. The paper highlights the importance of proving the accuracy of these methods due to complexity of distributed systems. It shows how these detection methods can be applied practically in real-world database environments. The analysis explores the trade-off each method, particularly focusing on their scalability and reliability.
The fourth research paper, Pulse, is a dynamic deadlock detection mechanism developed at Duke University. It addresses the problem that deadlock occurs when multiple processes wait indefinitely on each other, often in concurrent programs. Pulse uses speculative execution to detect complex deadlocks that traditional methods might miss, especially those involving consumable resources, example semaphores, pipes, etc. The operation that it performs is that it runs as a system daemon, periodically scanning for blocked processes and speculatively executing them to map dependencies into a resource graph. Deadlocks are identified by locating cycles in the constructed resource graph. Pulse was tested on classic deadlock problems, example dining philosopher and smokers, and a real-world Apache web server scenario, detecting deadlocks within 3 seconds. It has minimal impact on non-deadlocked applications and complements existing deadlock detection tools, enhancing the detection scope for multi-threaded systems.
Now we will discuss about our fifth research paper, which is UNDED, Deadlock Detection and Prevention. UNDED is a tool designed to detect and prevent deadlock efficiently with minimal runtime overhead. The tool logs only unique log dependencies, which reduces data storage requirements significantly. It prevents future deadlocks by merging the problematic logs in single log to break the cycles. Tests indicate that Undead performs better than other tools like Dimnix by producing fewer false positives. The tool is designed for continuous operation in production environment, ensuring minimal disruptions to systems. It is scalable and suitable for use in large real-world software systems.
So the sixth research paper focuses on the methods to detect deadlocks in distributed object systems using object middleware like Corba, EJB, and RMI. CORBA is Common Object Request Broker Architecture, EJB stands for Enterprise Java Beans, and RMI is Remote Method Invocation. So the problem that it focuses includes liveness issues such as deadlocks arise in distributed systems due to parallelism, synchronization primitives, and threading policies. The approach leverages UML stereotypes to model synchronization and threading primitives in distributed object systems designs. Formal representation includes UML diagrams that are translated into process algebraic representations, enabling formal analysis of system behavior. The translated models are analyzed with model checking tools to detect potential deadlocks by exploring the system's state space. Detected deadlocks are mapped back to the original UML diagrams, offering developers useful insights for system design improvements. So the application includes a stock trading system which serves as a case study demonstrating how UML diagrams, process algebra, and model checking work together to enhance system reliability.
Now we will be discussing about our seventh research paper, which is a priority-based algorithm for deadlock detection and distributed data. Now we will be starting with our seventh research paper, a priority-based algorithm for deadlock detection and distributed databases. This paper introduces a priority-based algorithm for detecting and resolving deadlocks efficiently in distributed databases. The algorithm uses an edge chasing technique rather than constructing a global wait for graph, which speed up the process. It assigns priority to transactions to reduce the number of messages needed and to avoid false deadlocks. When a deadlock is detected, the algorithm resolves it by aborting the lowest priority transaction involved. The method supports various transaction types, making it versatile and adaptable to different scenarios. Experimental results show that algorithm is effective for use in real-world database systems.
So the eighth research paper provides an overview of techniques for detecting and resolving deadlocks in distributed systems. A deadlock occurs when two or more processes are stuck waiting for resources held by other processes, and it affects performance and throughput of the system. Deadlocks are identified using tools like Wait for Graph, which visualizes process resource relationships and identifies deadlocks by detecting cycles. After detection, deadlocks are resolved by aborting one or more processes to free up resources. The algorithms for selecting processes to be aborted use metrics such as timestamps, burst times, and degree. The combinations of criteria include efficient resolution strategies that may combine multiple criteria, example, timestamp plus burst time, to reduce system disruption. The VSG algorithm, that is victim graph and suspension algorithm, aims to resolve deadlocks by cooperatively suspending and resuming transactions within a deadlock cycle, thereby minimizing disruptions.
Now we will be discussing about our ninth research paper, which is on parallel deadlock detection algorithm (PDDA) and hardware implementation (DDU). The PDDA and its hardware implementation, the DDU, are designed to provide fast deadlock detection for real-time multiprocessor systems. The DDU uses a Boolean matrix representation for efficient detection, improving speed by over 99% compared to software-based methods. The PDD algorithms avoid tracing cycles, making it both efficiently and scalable for complex systems. Test confirms that PDDA and PDU performs well in high concurrency environments, ensuring reliability. This is suitable for real-time applications that require quick and efficient deadlock management. The hardware-based approach ensures efficient resource management as systems become more advanced and complex.
The 10th research paper, titled Reviewing and Analysis of the Deadlock Handling Methods, it was published in the International Journal of Computer Science and Network Security in October 2022. It focuses on various approaches to handling deadlocks, specifically within operating systems, comparing multiple algorithms for prevention, detection, recovery, and avoidance. The paper highlights significance of deadlock handling, nothing that deadlocks can halt system operations as processes wait indefinitely for resources held by others. The strategies include prevention, avoidance, detection, and recovery. Effectiveness of this paper proves that prevention methods are identified as most effective, solving approximately 47% of reviewed cases, followed by detection methods and recovery methods that follow 28% of problems, and finally avoidance, that is 25%. The authors discuss various algorithms and techniques, including use of Petri nets for prevention, timestamp mechanism for avoidance, and queue-based detection for real-time applications. While prevention techniques are most effective, the paper suggests that ongoing innovation in detection and recovery methods is crucial for scalability and applicability, particularly in complex systems like distributed database and cloud computing.
Now we will be discussing about our 11th research paper, which is Sammati, Deadlock Avoidance for POSIX Thread, where POSIX is our Portable Operating System Interface. Sammati is a runtime system developed to automatically detect and fix deadlock for POSIX thread applications. It operates without requiring modifications to application source code, making it ideal for existing software. Sammati manages memory updates within critical section to ensure locks acquisition remains deadlock free. When a deadlock is detected, the system rolls back and restarts the affected thread, allowing the program to continue run smoothly. Evaluation demonstrate that Sammati is efficient and minimal memory overhead, making it practical for real-world applications. The system provides a reliable and low-impact solution for managing deadlocks in multi-threaded programs.
The 12th paper, titled A Compositional Deadlock Detector for Android Java, discusses a static deadlock detection tool developed for Android Java applications at Facebook. The detector aims to identify potential deadlocks during code reviews, focusing on modified code and its dependencies to provide quick feedback to developers within 15 minutes. It models programming languages as abstract programs considering rent locks, non-deterministic iteration, and non-recursive procedure calls to assess deadlock risk based on critical pairs of program threads. A deadlock is detected when there are conflicting lock acquisitions between program threads. The tool is integrated into Facebook's Infostatic Analysis framework and has been utilized in production for over 2 years. The system has reported deadlock fix rate of about 54% from over 200 deadlock reports, proving effective in large-scale, continuously evolving code bases. By analyzing changes incrementally instead of performing whole program analysis, the tool ensures scalability while emphasizing the reduction of false positives to main developer trust and efficiency.
Now we will be discussing about our 13th research paper, which is based on some deadlock properties of computer systems. Richard C. Holt's paper explains deadlock in computer systems using a graph-based approach. The paper defines key concepts such as processes and resources interaction to build a unified theory of deadlocks. It introduces knots in graph, which serves as indicator of potential deadlock within a system. The approach allows for the development of efficient algorithm for detecting and preventing deadlocks. The research paper discusses how these methods can be applied to improve system reliability and manage resources more effectively. The graph-based model simplifies deadlock analysis, making it easier to create an effective algorithm.
The 14th research paper, MPI Runtime Error Detection with Must Advances in Deadlock Detection, focuses on improvements in detecting and preventing deadlocks in MPI applications. MPI is Message Passing Interface. The authors introduce Must, Marmot Umpire Scalable Tool, a runtime error detection tool aimed at enhancing scalability and efficiency in deadlock detection for parallel programming. Traditional deadlock detection tools face challenges in large-scale MPI applications due to complex communication patterns and runtime behaviors. Must employs a graph-based deadlock detection model called and/or, capable of handling a wide variety of MPI communication constructs, including those not well supported by previous tools. The tool optimizes deadlock detection by minimizing overhead in analyzing MPI operations, making it suitable for large systems. Must utilizes techniques like wildcard receive handling and non-blocking communication checks to reduce false positives and enhance scalability. The paper presents performance results from using MUST on standard benchmarks, demonstrating its potential effectiveness for real-world MPI applications.
Now we will be discussing about our 15th research paper, which is DLOS, Effective Static Detection of Deadlocks in OS Kernels. DLOS stands for Digital Library Operating System. It is a statistical analysis tool designed to improve deadlock detection in OS kernels. It analyzes code path without executing them, allowing it to identify deadlocks that runtime methods might miss. DLOS uses advanced techniques to filter and identify locking patterns, which helps reduce false positives. Tests on Linux kernel show that DLOS is effective in detecting real deadlocks, including previously unknown ones. The tool is scalable and works well for large complex OS. DLOS provides a practical and reliable solution for maintaining stability in OS as they evolve.
The 16th research paper examines deadlock problem in multi-programming and distributed systems, specifically in resource management for operating systems and databases. It identifies the four conditions for deadlock: mutual exclusion, hold and wait, no preemption, and circular wait. The paper outlines three deadlock handling strategies: prevention, avoidance, and detection with recovery. It highlights unique deadlock issues in database due to concurrent data access and the need for maintaining consistency. The proposed online detection method identifies deadlocks as requests are made, advocating for an integrated approach that combines various handling techniques for complex systems.
Now we will be discussing about the future scopes of our research paper. Uh, First, improvement of real-time systems. The development and implementation of efficient deadlock detection algorithm like PDDA and DDU can efficiently enhance real-time systems, ensuring faster detection and better performance, particularly as systems become more complex. Second, the hardware software integration. As multiprocessor systems on chip MPSoC continue to evolve, integrating hardware units for deadlock detection and avoidance is crucial. This integration are expected to improve system reliability and efficiency, further reducing processing times. Third, scalability in distributed systems. The methods discussed for distributed systems, such as priority based algorithm and hierarchical deadlock models, show promise for expanding the scalability and reliability of database management in large scale and cloud computing environments. Fourth, advancement in concurrent programming. Tools like Undead and Dreadlock, which focus on efficient deadlock detection and prevention in software, highlight potential advancement in concurrent programming. These tools could be adapted to broader software systems, enhancing multi-threaded application stability. Fifth, application in software transactional memory. Uh, Algorithms such as Dreadlock have potential application in STM systems, which should be further explored to minimize resource allocation and minimize deadlock in complex environments.
Sixth, adoption in Android and mobile systems. Deadlock detection tools like DLOS can be adapted for Android and other mobile OS to ensure stability in evolving code bases. Static and dynamic analysis expansion. Combining static DLOS and dynamic pulse methods offer a comprehensive solution for robust error detection across various OS environments. 8. Integration with modern cloud and edge computing. Deadlock management techniques can be adapted for scalability efficiency in cloud and edge computing architectures. Ninth, broader applications in parallel programming. Enhancements in tools like MUST for MPI applications indicate potential for optimizing resource use in parallel programming. 10th, framework development for automated deadlock prevention. Advancements like Sammati can lead to automated frameworks that prevent deadlock across multiple programming languages and platforms.